31,600 kilometers. That is 19,640 miles. And it is how close a 340-meter asteroid will come to the surface of the Earth at 45 minutes past 9 in the evening Universal Time on Friday the 13th of April, 2029. Geosynchronous satellites orbit at roughly 35,786 kilometers, 22,236 miles. Do the subtraction and the asteroid named Apophis will pass beneath our own communications infrastructure? Not near it, beneath it. Here is the part that should stop you. This is, by a wide margin, the most precisely tracked asteroid in human history. Astronomers have its orbit pinned down to a level most planetary scientists would call absurd. And yet, right now, in the middle of 2026, nobody can tell you with confidence how fast Apophis will be spinning 3 years from today. Not roughly, not within a comfortable margin. The orbit is a solved problem. The spin is not. That gap between what we know to the meter and what we cannot pin down to the hour is the whole story tonight. By the end, you will understand why an object we have watched for 22 years is currently tumbling in a way that defies simple prediction, what Earth's own gravity is about to do to it, and why the same flyby that ends any lingering fear of impact is also the reason 2 space agencies are racing to get hardware to the scene in time. Start with what Apophis actually is, because the name carries more baggage than the object deserves. It was found on the 19th of June 2004 by Roy Tucker, David Tholen and Fabrizio Bernardi, observing from Kitt Peak National Observatory in Arizona. They only had 2 nights before technical trouble and weather shut the campaign down, and the asteroid was briefly lost. It took a separate team at Siding Spring Observatory in Australia, picking it up again later that year to nail the orbit down enough to realise what they were looking at. The object is roughly 340 metres across, 1,115 feet with a long axis stretching past 450 metres, about 1,480 feet. NASA describes its shape as peanut-like, likely 2 lobes stuck together, close to the length of an NFL football field and roughly the height of the Eiffel Tower. It is, in the driest technical sense, a rubble pile, a loosely bound aggregate of rock and dust held together mostly by its own weak gravity, not a solid boulder. For about 18 months after discovery, Apophis was the most alarming number in planetary defense. By December 2004, the best orbital fit gave it a 2.7% chance of striking Earth on that same April date in 2029. For a few weeks, it carried the highest hazard rating ever assigned to a real asteroid on the Torino Impact Hazard Scale. Then more observations arrived, the orbital uncertainty shrank, and the 2029 impact possibility dropped to 0. What lingered a little longer was subtler. A keyhole, a patch of space only about a kilometre wide that, had Apophis passed through it in 2029, would have reset its orbit onto a collision course exactly 7 years later, in 2036. It took until 2006 for astronomers to rule that keyhole out with confidence, and until 2008 to pin its width down to under a kilometre. Both the 2029 and 2036 impact scenarios are closed. That part of the story is finished, and it is worth being precise about that because it is not the part that is still open. What is still open is what the flyby does to the asteroid itself. And to understand that, you first need to understand how Apophis is currently spinning, because it is not spinning the way most asteroids do. In December 2012, Peter Pravec and a team of collaborators began a run of photometric observations, tracking how the asteroid's brightness rose and fell as it rotated. A simply spinning body produces a clean, repeating light curve, one period, over and over. Apophis did not do that. Its brightness pattern needed 2 overlapping periods to explain, a sign that the asteroid is tumbling rather than spinning cleanly around a single axis. The technical term is non-principal axis rotation, but the plain description is a football thrown with a wobble instead of a spiral. The object rotates, and that rotation itself slowly cones and drifts, so the same face never lines up with the Sun on a simple schedule. Pravec's team found 2 periods locked together, a precession period of about 27.38 hours and a rotation period of roughly 263 hours, in what specialists call a short axis mode of tumbling. The wobble angle runs 20 to 25 degrees, what researchers class as moderate excitation. It is not violent, it is also not going away on its own anytime soon. Picture a top spun slightly off-center. It still turns, but the whole axis of that turning slowly cones around, tracing a second slower circle on top of the fast one. That is the short axis mode Pravek's team documented, 2 clocks running inside one object, and it is why a single rotation period was never going to describe Apophis correctly. The asteroid is close to what physicists call its lowest energy rotation state, sitting only 2 to 3% above the true minimum, yet even that small excess is enough to keep the wobble alive for a very long time, because there is almost nothing inside a loosely bound rubble pile to damp it out quickly. Energy bleeds away through tiny internal friction, grain grinding against grain, and that process is slow. Left alone, it can take longer than the time since the tumbling began. Apophis is not being left alone. Here is where the cause and delay problem comes in, because tumbling is exactly the kind of state that gravity can reach into and rewrite. On the 13th of April 2029, as Apophis passes inside the ring of geosynchronous satellites, Earth's mass will exert a tidal torque on the asteroid strong enough to plausibly change its rotation outright. A 2023 analysis by Connor Benson and colleagues put a number on it. The precession period could drop from roughly 30.6 hours to somewhere near 21 hours, and the longer rotation period could fall from about 265.7 hours to somewhere near 185 hours. The asteroid spinning up rather than down. Other modelling groups, working the same problem with different assumptions about the asteroid's internal structure, get a wider spread. Changes anywhere from 10 hours slower to 15 hours faster, with some runs suggesting the effective spin rate could double or halve. The honest summary is that the exact outcome depends on Apophis's orientation at the precise moment of closest approach, and that orientation is currently the least well-constrained number in the entire problem, because the asteroid is already tumbling in an orbit we cannot extrapolate with confidence 3 years out. A recent modelling paper published in Astronomy and Astrophysics this year found at least 3 different combinations of precession and rotation period that fit the existing photometry equally well. 3 different clocks, all claiming to describe the same rock, and no data yet to say which one is right. That uncertainty is not academic. A team led by Ronald Ballouz published an analysis in 2024 arguing that Apophis, already tumbling, may be unusually susceptible to what they call a tumbling refresh mechanism. The tidal shaking of the 2029 encounter, mobilizing loose surface material, triggering small landslides, and exposing regolith that has never seen direct sunlight. Richard Binzel, presenting related work at a planning workshop earlier this year, put it about as plainly as a scientist allows himself to. Earth's gravity may stretch and squeeze the asteroid enough to expose pristine material beneath its weathered surface, or it may do almost nothing, and right now nobody can tell you which. The historical precedent for tumbling itself is not exotic, which matters, because it is the piece most likely to get misread as a sign that something is wrong with Apophis. Comet Halley tumbles, asteroid 4179 Tutatis tumbles. The interstellar visitor Oumuamua tumbled so severely in 2017 that it briefly became one of the most discussed objects in astronomy for that reason alone. Out of nearly 20,000 asteroids with reliably measured rotation in the Asteroid Light Curve database, close to 500 show this same non-principal axis signature. Tumbling is usually the leftover signature of some past event, a sub-catastrophic impact. The slow torque of sunlight itself through what is called the Yorp effect, or, in rarer cases like this one, a planetary flyby generations ago that never fully damped out. It is a state, not a symptom of instability, and it does not imply the asteroid is coming apart. Now clear out the noise, because Apophis draws 2 very different bad readings, and both deserve a direct answer. The first is the zombie version of the 2004 scare, the claim that circulates every year or two that Apophis is secretly going to hit Earth after all in 2029. dusted off from the same 2.7% figure that was retired 2 decades ago by better radar data, most notably tracking from the Deep Space Network's Goldstone complex in California and the Green Bank Telescope in West Virginia in March 2021. That data point and everything gathered since keeps Apophis off every current risk table. There is no scenario in the present orbital solution where the 13th of April 2029 ends any other way than a close, safely observed pass. The second bad reading takes the tumbling itself and turns it into a story about a shield failing or an object destabilizing. It is speculation, not consensus, and the actual literature says close to the opposite. Tumbling asteroids are common, well studied, and Apophis has been documented in this state since 2014, 15 years before the flyby that supposedly caused alarm about it. The wobble is not new. What is new is that Earth is about to reach into that wobble and change it on purpose, by gravity alone, and scientists are positioning hardware to watch it happen in real time rather than guess afterward. That positioning is the part of the story with actual dates attached, so treat this as the checkpoint list. Ground-based photometry through 2027 and 2028 is the near-term item that matters most, because researchers writing in this year's astronomy and astrophysics paper argue that pre-encounter observations in exactly that window are what will finally break the tie between the competing spin models, resolving which of the 3 current best fit solutions is correct before the flyby arrives to complicate things further. On the far side of the encounter, NASA's OSIRIS-APEX spacecraft, the retasked OSIRIS-REx probe, is scheduled to arrive at Apophis in late June 2029, close enough behind the flyby to measure the afterstate directly rather than reconstruct it from telescopes. The European Space Agency's Ramses mission is aiming for the opposite timing, a rendezvous before the encounter, so that its instruments are already in position to accompany the asteroid through the flyby itself, recording the tidal event as it happens, rather than its aftermath. On the ground, the flyby carries its own precise schedule. Peak brightness near 2035 Universal Time, magnitude around 3.1, and closest approach at 2145 Universal Time, with the United States Geological Survey noting that a close pass of an object this size is a rare event, occurring only every few thousand years on average. Roughly 90% of the world's population lives somewhere Apophis could, in principle, be seen without a telescope. That evening, weather and light pollution being the only things standing in the way. As it crosses the sky, it will move fast enough to notice, up to 42 degrees per hour at closest approach, close to 1 moon width of sky every minute, before it climbs back out toward daylight and, on the 14th of April, passes within about 95,000 kilometers of the moon itself. The encounter leaves a mark on the orbit as well as, possibly, the spin. Earth's gravity is expected to widen Apophis's path around the Sun enough that it graduates from the Aten class of asteroids, orbits narrower than Earth's own, into the Apollo class, orbits wider than Earth's. The rock that arrives in April 2029 and the rock that leaves it will be dynamically a different object, in trajectory at minimum, and quite possibly in rotation and surface as well. Hold both of the following at once, because both are true and neither cancels the other. Apophis poses no impact risk to Earth in 2029, in 2036, or in any presently modelled future encounter, and that conclusion is as settled as anything gets in planetary defence. At the same time, the precise physical state that same asteroid will be left in after Earth's gravity finishes with it on the 13th of April 2029, its rotation period, its surface, whatever material gets shaken loose and exposed, is genuinely unknown, and will stay unknown until instruments already being built and launched are actually there to measure it. The danger is closed, the physics experiment is not. Both of those sentences belong in the same story, and only one of them makes headlines. We will be tracking it.